Alright, so in this tutorial we're going to summarize the concept of mirror images, of which we talked about in class the other day and you started a lab with today in regard to plane mirrors. The first page is going to sum up what we did yesterday with concave and convex mirrors, and then you can stop at that point if you want. I'm going to continue and summarize the key things about plane mirrors, which you're investigating with the lab, so we can always pick up on that later. So I want you to remember back to yesterday or 2 days ago when you were looking at that pig and you saw that projection of the pig at the top of that hole. Okay, and if we had gone outside, we'd see something similar or feel something similar with the sun. What exactly did you see when you're looking into it? And we said that the correct term, even though we often say reflection, is an image. And it's a particular type of image. So we want to understand why an image forms. And for a concave mirror, it happens for a different reason than, let's say, for a plane mirror, but at least it gives us a more concrete idea. Okay, so the concave shape of the mirror, concave means it caves in, reflects light in such a way that all the rays focus, okay, or a fancier term is converge, at a point in front of the mirror. In other words, the image is actually in front of the mirror. So I'm going to show you with a ray diagram. I did this in class briefly, so here's where it's going to be a little bit more formal. So I'm going to use the line drawer on the smartboard. So let me just do that. Okay, so I have at this arrowhead right here, we've got 3 rays of light coming from there. Okay, and those rays of light are hitting the mirror at 3 different places, and they're going to reflect off them. So I'm going to use some rules, essentially the law of reflection, to show how those rays of light reflect. So I've drawn a normal for this first parallel ray, and so I'm going to try to draw a ray of light that is equal to that angle as closely as possible. In other words, this angle, here's my theta I, and here's my theta r. You don't have to draw that in, but you should recognize it right now. So there is that dark ray there is reflected ray. Okay, my next ray that I can do is the one that passes through this dot. It hits the mirror here, and then it should follow, reflect back, okay, such that, again, the angles are very similar. Whoops, I lost the thread of the line there, so let me pick that up and draw it so it's like this. Okay, in other words, if you're following along here, and if you have a straight edge, that'd be great. You'd want this second reflected ray to be parallel to this line right there. I've chosen it such that this is my R2, if you will. Here is R1. And if I look at a third ray, okay, actually I'm going to ignore that third ray, but the way it would bounce off, I'll take that back, I'm not going to ignore it, but it would reflect off at this point, and if we did things right, it would reflect right back like that. So we can see, and I'll call that R3. So if you look at R1, R2, and R3, they all intersect at this point right here. And so that's where your eye is going to see the image of the arrowhead. And if we do the same thing with the tail, I'm not going to go through all the rays, we would find that the image of the tail forms right there. So if I connect the two, I realize here is the arrowhead, here is the tail, and that's my image. Okay? And we can talk about the properties of that image. So let's summarize right below. This type of image is called a real image. Why is it called real image? Because it's the result of light actually coming to a focus. Light is really there. Okay, if you look at it through the mirror, you will see that's where the image is. If I were to put a screen right here and have the mirror there, the image would form right on that screen. So let's talk about other properties. All right, in other words, how big is it, where is it, etc. Depend on 2 important parameters. The curvature of the mirror, so if we change the curvature of the mirror, the image will form elsewhere, and the distance of the object relative to the mirror. We're not going to get into great detail, but if I were to move this object from there to, let's say, further away, then the image would form closer to right here. If I were to move this object closer to the mirror, the image would move further away. But we don't have to know all those details. I just want you to get an idea of what an image is and why it forms. Okay? And an important property of this image is it can be projected onto a screen. So there's a lot of uses of that, especially with telescopes. Now, if we look at a convex mirror, it's a little bit more complicated. I'm not going to spend a ton of time on it. But the important thing about a convex mirror is that light never converges in front of a mirror because a convex mirror is a diverging mirror. All right, and so that's what's trying to be. So when I showed you on the board the other day, if this is a convex mirror and light comes in, let's say parallel light, okay, what it will do is it will spread out, diverge. So this particular diagram here has a bunch of rays drawn. It's already done for you what I was talking about. So again, you don't have to know every single detail, but let me just give you the highlights. If I look at a pencil, here is one ray that comes in and it reflects that way following the law of reflection. So I do expect you to recognize how that will reflect when it hits that type of shape. The other ray that they've drawn in is this one here, and it bounces off and reflects that way, again following the law of reflection. And the key thing is these two rays will converge, or they seem to originate back here, and so your eye will see the image of the pencil back there. Now, these light, there's no light actually behind the mirror, but your eye thinks it, so it's not going to be a real image. So they seem to originate, sorry, repeating myself, from behind the mirror. And because light does not actually come to a focus there, in fact, it never comes to a focus, this is called a virtual image. So I want you to know that term. It's really an image, but there's just no light there. It just seems like light is coming from there. So that's the difference between it and a real image, where light really does converge. Okay, at this point you can stop. This is all as far as I wanted you to get. I'm going to continue on and summarize what we're investigating right now with plane mirrors. Okay, so what do we get when we have a plane mirror? You should have done this with the lab or started. So if I have an object that's in front of a plane mirror, I've drawn 3 random incident rays. And so what we're going to do is crudely estimate what the reflected rays look like. So I've drawn normals for each of them. So this one's pretty straightforward. It comes in at a 0-degree angle to the normal. So it's going to go out at a 0-degree angle. And as best as I can do it, it's going to go straight back. Okay, then this ray that coming on the top part of it, it hits at a small angle, so I'm going to try to get it to go at a roughly the same angle. That looks about good. And then if I do the same thing at the bottom ray, I'd say that's pretty good. So if I look at those 3 reflected rays, I notice that they're never ever going to converge out front. So I'm not going to get a real image like we saw for a concave mirror. But the eye that picks up this ray, and this ray will trace it back, that light rays, to a common point of origin. So let's see if I can do that with the smart board. So I won't use it here. I'll use let me try to use a dashed line. Okay, so I'm going to just extend this back. That's okay, not perfect. Extend this back. It should be good, but not great. And then I'll extend this back. Okay, so I didn't do a bad job there. But the point is, your eye will think the head of that arrow is right there. And if I do the same thing for the base of it, it will seem to form right there. And the key thing, what we want to understand about the image, so here's the image, is that it appears behind, sorry, that looks bad, is that it appears inside the mirror. And if we were to measure the distance of the object to the mirror and the distance from the image to the mirror, we should find they're the same distance. That looks pretty good to me. And if you look at the size of the image versus the size of the object, they look pretty close. So to summarize, an image always forms behind the mirror at the same distance as the object is in front of the mirror. That's an important point to remember. Since the light focuses, what is seen is a, guessed it, virtual image and cannot be projected onto a screen. The image size is equal to the object size. So if you're 6 feet tall and you're really close to the mirror, you will appear 6 feet tall, really close to the mirror. If you're standing very far away from the mirror, you'll appear smaller. That's perspective. It's not because the image size has changed. And the orientation of the image is the same as the object. Same as object in the vertical condition, but it is flipped laterally. In other words, left appears right, right appears left. We'll talk more about that in class. So then we can do an important example. This is something you're going to see on a quiz, so pay close attention. If you don't understand, come in with questions. So let's say I have a mirror as represented by the solid line, and I place the letter B in front of it. I want us to do two things. Where would an eye have to be placed to see the B in the mirror and draw the image of the B? So let's do the second part first. The rules from we learned above is that the image of the B is going to be inside the mirror. But it doesn't have to be confined within the boundaries of the mirror. That's a common mistake that's made. What we can do is we can extend the mirror line as if the mirror were really there. So I'm going to do that right now. So in other words, the mirror can be thought of as extending here. And now I can say, all right, the B is this far in front of the mirror. So I'm going to, the curved part. So I'm going to go the same distance there, estimated. Okay, I'm not going to get the ruler out. I'm a little off. Not a perfectly straight line. That's good enough. So the B is going to, the curved part is going to be there. I've made it a little too big here. That's a smart board. And then this part is a little further away, so I'm going to put it right there. Okay, now my image is a little bigger than the object, so you can make yours a little smaller, but that's what the image of the B would look like, and that's how you approach it. So where would you have to place the eye in order to see it? Well, if you place the eye right here, don't do that. Okay, any light coming from the mirror is not going to come from the dashed part. It's going to come from the solid part. So any light that's reaching your eye from the mirror must have come from over here. Okay, so I don't want to look there. I'm not going to, the B is right over here. So you can reverse that logic and say, all right, let me erase all this. Is any light from the letter B that's hitting the mirror must be coming from above. So I'll choose that line. So if I follow the law of reflection, then the light must reflect that way. Or perhaps it would do this. The point is, all light coming from the mirror is down here. So this is where you would put your eye. Your eye would have to be in the bottom part to see the image. Now I've done it fairly poorly, but it will trace it back to right there. Okay. So if you have any questions about that, don't hesitate to ask, but it's pretty straightforward.